So I'd like to talk about cubics a little bit. A cubic is a polynomial of highest power 3. The standard cubic go in this form, which you have on your screen. Ax cubed plus bx squared plus cx plus d is like quadratic with one additional term. You have the highest power third term, the dominant term. And you will often set this equal to 0, so I've just put in there. One key thing to note is that a cannot be equal to 0. If a was equal to 0, then we would not have a cubic. We would have a lower degree polynomial like a quadratic or a linear degree polynomial, which is a line. So a is not equal to 0 has to be assumed. All right. What does a cubic look like? We know what a line looks like. We know what a quadratic looks like. A cubic will have a general shape, as you can see on the graphs, depending on whether a is positive or is negative. A entirely determines the general shape of the cubic. This is general shape. This is not all cubics look like this. It's a general shape. So I should write general shape just so that you don't get confused, because you'll see some cubics which will differ from ones on your screen and you might be confused. So I'm telling you already, these are not exhaustive. Now on your graph, you can see I've marked the 3 roots. So roots are just x-intercepts, or where the function is equal to 0. So I've marked the 3 roots, as you can tell, and they will have a lot of relevance in a second when we read the notes about cubics, which is also visible on your screen. So let's move right into it. And I'll also tell you how the shapes of these cubics come about. So I'm going to talk about cubics right now. Cubic or cubics will have at most 3 real distinct roots. Now, you must understand what do I mean by real? Well, if you understand what is complex, you'll understand what real is. Real is your usual numbers. From like, the only thing is, what are complex numbers? If you have something of square root of -1, square root of -1, that's not a real number. That's a complex number. So don't think about it too much. Just think about what I'm saying. You can have at most 3 real distinct roots. Distinct means different. And this is true by fundamental theorem of algebra. I've written it as FTA. Oops. FTA. Fundamental theorem of algebra. So you can search that up if you want, but take my word that a cubic will have at most 3 real distinct roots. You can have roots which are repeated twice or thrice. I meant to say thrice, it got deleted. Repeated twice or thrice. For example, if I have the equation y equals x cubed, 0 is a triple root. It's the only solution and it is times x, so 0 is a triple root. In y equals x squared x plus 2, 0 is a repeated root by same logic. Now, real and complex roots will make up all the 3 roots. I should write 3 roots. A cubic will always have 3 roots, but some of them will be real, some of them will be complex. The complex ones you will not be examined in the exam. That's for further maths. But it is good to know that the roots are made up of real and complex for the sake of your crystal clear understanding. So you cannot have only 2 real distinct roots unless one of them is repeated. Now why is that? This is where you need to know something important. If I have 2 real roots and I have something, and I know in total a cubic will always have 3 roots, real or complex, I know there has to be one complex root, right? You would think there has to be one complex root and we are done, right? One complex root. But this is where something important comes in. Complex roots never occur in odd number. They always occur in even number. You don't need to know the reason. You just have to take my word in. Complex roots always come in even number. So this situation is impossible. Possible situation. You cannot have 2 real roots and one as complex roots will always come in an even number, whether that be 0, 2, 4, 6, whatever. So this is just for your understanding. So you cannot have 2 real distinct roots and one complex root. What you can have is one root is repeated twice. So let's say if I have 3 and 5 as my roots, let's say the equation is y equals x minus 3 squared x minus 5. This is completely acceptable. This is a normal cubic. Completely possible. You have 3 repeated twice and you have x minus 5. Hopefully you understand. In other words, what I'm saying is, if you have an equation like y equals x plus 1, x minus 2, and you need to get a third root, That third root would be, let's say, x minus some real number. Some real number. That's what I'm trying to say. It will not be a complex number for a cubic, never. Hopefully you guys understand what I've just told you. If not, you might want to go back a little bit and slow down as I was saying these things so you can adjust the speed. And I'll now move on to sketching cubics. Now we are on to sketching cubics. This is nice. It's a fun part. And there is one more thing you would need to know, which is whenever we are going from one root to the other, there will be a turning point in between. What is a turning point? A minimum or a maximum. So whenever I'm going from one root to the other, the graph has to pass through all the roots. Whatever roots the cubic has, the graph has to pass through all of them by its nature. With that, you will get a turning point whenever you go from one root to the other. Same is true here. As you go from this root to this root, you get another turning point here. Now, will you always know where the turning point is when you're sketching? No, you can calculate it, but not always would you be required to calculate the turning point. But you should understand when you're going from one root to the other, you will always have a turning point. And then you realize something about cubics. Cubics can have 0 or 2 turning points. They cannot have 1, only 0 or 2. Now, why is that? Why is that? Suppose if I have a cubic and let's say I'm drawing something like this, I get 1 point, right? I get 1 point, 1 turning point. Let's say it meets my second root somewhere here. And now you are claiming that this is the only turning point which will ever be in this cubic. If that were true, how would we get the general shape? How would you continue towards infinity as we are right here? How would you continue towards infinity? You can check in this example as x goes to infinity, f of x goes to infinity, right? Because as x gets large, assuming a is positive, we assumed for this graph a is positive, f of x will go to infinity, right? You can plug a number like 1,000,000 or something and you'll realize. But if I have my graph right here and I claim this is my only turning point, how can I ever go to this direction when my graph is continuing downwards? I would need another turning point, right? So if I have 1, I will have to have 2. It's not possible for me to only have one single turning point. I can have 0 turning points. How will I have 0 turning points and get the same shape? That's actually seen pretty easily from the graph of y equals x cubed. It is actually something like this. Y equals x cubed. So your only root is x equals 0, right? So you don't need to go to multiple roots. You can only get something like this. And the graph only changes concavity. It doesn't get a turning point. This is a point of inflection. So it's not a turning point. Point of inflection. It has 0 turning points. This graph only has a point of inflection. You understand that now? So you can have 2 turning points, which is most common. As you can see here, 2 turning points are most common. You can also have 0 turning points, as you just saw. And the last thing you need to understand is the concept of behavior towards infinity. So I'm going to write the equation of the cubic once again and try to be more clear about this. F of x equals ax cubed plus bx squared plus cx plus d. A is not equal to 0. Good. And now we must understand that whether this graph goes to, we need to determine the behavior as x goes to infinity. But how would we determine that? It all depends on this term. This is the dominant term of the cubic. This will determine what the whole cubic does. These terms are somewhat irrelevant when we go to a higher number for x. For example, I can say as x tends to infinity, I can say, then f of x is approximately equal to ax cubed. Would you agree? Ax cubed becomes so large as x becomes large that bx squared plus cx plus d are, let's say, not significant enough. So if a is positive, if a is greater than 0, then this would go to infinity, right? This would also go to infinity because a is positive. If a was negative, if a was negative, then this would go to negative infinity, right? As x is going to infinity, you have that negative sign from the a and you go to negative infinity. So hopefully you understand that. And you can do a similar logic for negative infinity as well. As x goes to negative infinity, you can do a similar logic. Whatever the sign of a is, we can determine where the graph will go. We'll look at that in a few examples. Right, I think that's all the necessary concepts. And now we can actually look at sketching. We can look at rules of sketching. So now we are going to sketch some things, and we have rules of sketching cubics. You have to find the x-intercepts. So if you have a graph, you want to find the roots, x-intercepts. You want to find the y-intercepts, where the graph hits the y-axis. And you need to see whether the graph goes to positive infinity or negative infinity as x becomes very large or very small. Okay, these are the only things you need to do. So these are the only things you need to do, and hopefully that's clear. Let's get started with the example. You need to sketch y equals x plus 1 and x minus 1. Now what are the roots? Let's write the roots. Roots, they are 0, 1 and negative 1. You can just equate this to 0 to see what the roots are. And so if we had a sketch, I think I should make it a bit bigger. Something like this. This is your x, that's your y, and your roots will lie on 0, 1 and negative 1. I think I should expand the x-axis a little bit. Yes, so there we go, x, 0, 1 and negative 1. Now, if I put x equals 0, I need to find the y-intercept now. So this is done, we've done the first part. We need to find the y-intercept. Plug x equals 0, so if we put plug x equals 0, we get y equals 0 because this term will make the whole expression 0. So the graph goes through here, 0, 0, the origin, which is very convenient. We have the y-intercept as well. So that's done too. Excellent. And we just need to say behavior at x. We need to determine whether in this expression, the ax cubed term, is it positive or negative? In essence, we need to determine whether a is positive or a is negative. How do we do that? Notice, I should put that back in. Notice that the cubic term will come from x squared multiplied by x. And all the coefficients of x are positive. So we'll get a positive cube term. That means the general shape of the graph will look something like this. Okay, now let's put the roots back in. Let's try to draw this. We also know that since there are 3 distinct real roots, there will be 2 turning points. To go from one root to the other, you have to go through a turning point. And I know as x tends to infinity, f of x will tend to infinity. As x tends to negative infinity, f of x will tend to negative infinity because a is positive as a is greater than 0. In this case, it would be 1. Yes. So now let's draw the graph. So I'll start from the negative infinity part. I will hit my root. I know somewhere there will be a turning point. I don't know where it exactly will be. I'm not required to put that. Then I hit 0. I will keep going down. And then I know I have to turn back up again. I don't know where exactly that will be. I have not calculated that. You are not required to right now. So you will turn and you go back up towards infinity. So you see how simple it is now to construct quadratics, not quadratics, cubics. Hopefully that is clear. Let's look at another example with a repeated root. So suppose you were asked to sketch something like this. How would you do it? Let's say y equals x plus 1 squared times x plus 3. What would this one look like? Let's go back to the sketching. Let's use the same 3 rules. So we're going to find the roots, x-intercepts, right? Your rules here. Find the roots, y-intercept, behavior. Okay, what are the roots? Negative 1 and negative 3. Negative 1 is a repeated root, you can tell. And then what is the y-intercept? I'm going to mark negative 1 first. And then I'm going to mark negative 3. There we go. Oops, the pen just stopped working. Yeah, there it is. And we're going to find the y-intercept. What will that be? Plug x equals 0. We get 1 squared times 3. which is just 3. So the y-intercept is 3. Hopefully you can see that, right? Okay. We know the graph will go through all these points, and we know there is no root on the other side. Why are there only 2 roots and not a third one? Because one root is repeated. Okay, good. Let's mark the y-axis, let's mark the x-axis, and now let's decide how the behavior is. Again, we know there will only be a positive term because all the x coefficients are positive. So a will be greater than 0 in ax cubed. So you know how the graph behaves by now. It will take this shape. I will start from negative infinity. I will turn somewhere. I will go back up here. But to reach 3, I need to turn up again, and then I need to continue. And I'll only have 2 turning points now. I won't have 3 because then that would make it a something else. It would make it a quartic. So 2 turning points like this. There we go. You can just determine where the graph needs to go, and then you can accordingly put the turning points in. Okay, great. So this is your basic cubic sketching. You also know the graph of y equals x cubed, which is just an inflection point like this. So this is y equals x cubed. This is an important graph to remember, because if you are asked to sketch something like sketch y equals x minus 2 cubed, if you know basic transformations, this is the exact same graph, but shifted by 2 units to the right. You don't need to do all the process. You can just do the same thing, but you can shift this graph a little bit to the right. This will be 2, this is 0, this is y, this is x. Exact same graph, just shifted by 2 units to the right. So this is the last example I want to look at for sketching cubics. This is a very important one because here we only get one root and it's not even repeated. So if you look at the equation, we have x minus 1 times x squared plus x plus 2. So we have this equation, we solve for it, and we only get one root. We don't get any root from this part since the discriminant here is negative. And from the quadratics chapter, we know that if a quadratic has a negative discriminant, it doesn't have real solutions. It only has complex solutions, but we are only interested in real solutions. In this case, the cubic has one real solution and 2 complex. It's not written here, but there are 2 complex. You can't graph complex solutions on real axis. These 2 are real axis. So you can't do that. So it's not even required, but just for your information, it's there. Okay. Now we have x equals 1. We need to find the y-intercept as we were doing all along. What is the y-intercept? We see y-intercept is negative 2. Excellent. We got our root. Excellent. And we need to see what the behavior is as we go to infinity. So we get the cubic term from here. We get x cubed. We know it will be positive because both the coefficients are positive. So as x goes to infinity, f of x will go to infinity. As x goes to negative infinity, y will go to negative infinity. Y and f of x are same thing in this case. So we have that. And the question arises, how do we exactly approach 1? Because we don't know how many turning points there are. We don't know if there are 2 turning points or if there is 0 turning point. We haven't calculated it. And in this case, there is no need to calculate. You can tell that even they have written, you don't have enough information to know whether the exact shape is this or what they have drawn. The key point here is that you have to go from negative infinity, you have to turn to positive infinity. Now you can go through 2 turning points, like this was also an option, and you will get something like this, or you could go like a point of inflection like they did. Since you were not asked to calculate the turning points explicitly, you can assume it does either of them, as there is only one root which is a unique root. So you can assume it does the concave thing and not the turning point thing. You could have drawn the turning points, you would have still gotten the marks, unless they specifically asked you to find the turning points. So in this case, this graph is perfectly right. It goes to positive infinity as x goes to infinity. It goes to negative infinity as x goes to infinity. We have marked the roots, we have marked the y-intercept. That's all the examiner is looking for. If you really wanted to be precise, you could find the turning points. if there were at all. But that's not the scope of this chapter. That would be later on. So thank you very much. That's the end of this video.